Hello everyone, and welcome to today's chem lesson. Today we are going to talk more about solubility, looking at which attractions, which ions are more attracted to each other than they are to the water's polarity, right, than the pull of the water. We talked about this a very little bit last time, where we said these two ions are attracted to each other. They have an attraction. We're going to color it here in red. All right, the positive and negative are attracted to each other. But also, the water has slight charge with its polarity that attracts it to those ions as well. If water is stronger than this attraction, right, if the pull of water on those ions is stronger than this attraction, it will dissolve the substance. The substance dissolves in water. If this attraction between the ions is stronger than the attraction of the water, this substance settles to the bottom of the water and sits there in a lovely little pile, not doing anything, right? They do not interact. But we can't just look at a substance and say, oh yeah, that's not going to dissolve, or oh yeah, that is going to dissolve. We need to know more about the attraction. And because the math involved here is actually pretty intense, we actually just get a piece of the reference table that tells us whether or not the attraction between two ions is going to be stronger than that of water. This is where table F comes along. Right, this is table F taken directly from our reference table, blown up to take up the whole screen. And it has two clumps, right? It's got these two columns here, then a little separation, then these two columns here. The first column identifies ions that normally dissolve in water. These things are almost always soluble. And it pairs them with their exceptions. Things that then make them not follow the normal and not dissolve in water. For example, ammonium is something that is normally soluble and has no exceptions. So any compound with NH4 in it will be soluble, will dissolve in water, because nothing stops it from dissolving in water. On the other hand, something like chlorine, right? Cl- is almost always soluble unless you pair it with one of these three ions. NaCl, salt, is soluble, dissolves in water. AgCl is insoluble, it does not dissolve in water. Because silver is an exception for chlorine. Right? Chlorine normally dissolves, but when you pair it with an exception, it does not dissolve. On the other side of table F, our conditions are reversed. These things are normally insoluble. They normally do not dissolve in water. But if you pair them with their exceptions, they do dissolve in water. Now the exceptions column is a little bit more packed than it was before. Here, they all contain this chunk of text. Group 1 ions or ammonium, and those are these guys over here. Group 1 ions are your ions in the very first column of the reference table. They are always soluble with no exceptions, including these things over here. Right, so sodium carbonate. Right, sodium is a group 1 ion. That means sodium carbonate is soluble. Barium carbonate. Barium's in group 2. Barium carbonate is not soluble. So when we want to decide, when we want to look and see if something is soluble in water, we are looking at table F, trying to find one piece of our compound on here, and then checking to see if that is paired with any exceptions. Let's look at a couple of examples. Here we still have our lovely friend, table F, and we've got some compounds. And the question is going to be, are these compounds soluble? Let's start with sodium nitrate, NaNO3. I'll do this one with you. When we have NaNO3, we want to decide if it's soluble or not. We want to find Na or NO3, or both, on the first or third column, right, the starting columns of table F. Na is here, and NO3 is here. They just so happen to both be on table F. That's not always true. There will be at least one piece of the compound on table F. It does not have to have both of them. So here, sodium is soluble with absolutely no exceptions. Nitrate is soluble with absolutely no exceptions. So sodium nitrate is soluble. It will dissolve in water. What about iron chloride? When we look for iron chloride in our first and third columns, right, our list of ions, iron doesn't show up, and that's fine, but chlorine does. Chloride is normally soluble. Iron is not one of the exceptions, so iron chloride is also soluble. What about aluminum phosphate? Is aluminum phosphate soluble? When we look for aluminum phosphate in our main columns, aluminum doesn't show up, but phosphate does. There it is. Right, phosphate is normally insoluble. Aluminum is not one of the exceptions, so it follows its normal rule of being insoluble. It will not dissolve in water. Next up, barium hydroxide. Is barium hydroxide soluble in water? So, we look for barium hydroxide. Right, barium doesn't show up in the main columns, but hydroxide does. Hydroxide is normally insoluble, but what's that? Barium is an exception. So what would normally be insoluble is paired with an exception that would make it now soluble. Right, doing the opposite of what it would normally do. Last up, silver chloride. Is silver chloride soluble or insoluble? Will it dissolve in water? We already know where chlorine is, because we had it in a previous problem. So chlorine is normally soluble, but silver is paired, right? Sorry, silver is an exception, so it is paired with an exception, meaning it will do the opposite of the thing it normally does. Right, so it will be insoluble. It will not dissolve in water. Now, table F will never contradict itself. Right? For example, if I have something like Na2S, sulfide is on here, normally insoluble. Sodium is on here, normally soluble. But sodium is an exception for sulfide. So no matter which piece you look at, it will give you the same answer, that this thing is soluble. Right, that's always something that comes up. Everybody wants to know, well, what if, what if, what if? It will never contradict itself. To wrap us up for today, one final question. Based on reference table F, which of the following solutions would be the least concentrated? Now, this is a tricky English question, more than a super tricky chem question. I pulled the relevant piece off of table F for you. See if you could identify which one it is. When we look at a question like this, and we don't really understand what the question is asking, but they tell us something about a piece of the reference table, we can always play our favorite game, which of these things is not like the other. One of these things just doesn't belong. Table F, as we learned today, tells us about solubility. Right? Whether something dissolves in water or not. So ignoring whatever the question is asking for right now, I look at these four choices, all four of these sulfates, and I need to pick out which one of them is different from the rest based on table F. Table F tells me that these first three are soluble, and the last one is insoluble. Right, there's barium, our lovely exception here. If you had to guess on this question that asked you about Table F and gave you 3 soluble things and 1 insoluble thing, guessing the insoluble thing would be the right move. But what is this question even asking? Right, this is a tricky English question more than anything else. Right, already accepting that number 4 is the right answer, let's take a look at the question itself. Which of the following saturated solutions would be the least concentrated? Right, what does concentrated mean? When you think about orange juice, which comes from concentrate, when you think about something that is a very concentrated liquid, it has a lot of stuff in it. Right? Something that is concentrated has a lot inside it. So when we want something that is the least concentrated, we want something that has the least amount of stuff in it, the least amount of dissolved stuff in it. Which means it's not going to be any of the 3 that dissolve in water. Since they dissolve in water, they have contributed to the concentration of the water. But something that does not dissolve just sits on the bottom and does not dissolve. Right? So it does not contribute to concentration of the water. Concentration itself is going to be a thing that we talk about near the end of this unit, but I pulled this question out specifically to show you that even if you don't truly understand the question, getting a piece of the reference table and knowing how to read the reference table gives you the answer here. Right? One of these things is not like the other based on reference table F, which they even tell you in the question. And with that, I'm going to transition us over to our Zoom meeting for questions, comments, concerns, and attendance. And I will see you there.